Hello there and welcome back to Chemist Tea Time. In today's discussion, we are going to be revisiting chemical equations and learn how they can be a powerful tool to predict the outcome of a reaction. We're going to focus on using balanced chemical equations to predict the amount of a substance that is consumed or produced by a chemical reaction. As a reminder, this process is referred to as stoichiometry. We will also introduce the concept of actual and theoretical yield, as well as limiting and excess reactants. When dealing with stoichiometry, the first and most important step is to ensure that we are starting off with a balanced chemical equation. If we are not presented with a balanced equation, we first need to go through the steps of balancing it before we can proceed. This step is important because the chemical coefficients show us the ratios of each different type of atom or molecule that are participating in the reaction. Once we have this balanced equation, we can use it to predict the amount of substance that is produced or consumed in that reaction. Another important consideration is that when converting between the quantities of different substances, we always need to first convert the quantity into moles. This is a critical step because the number of moles of a substance reflects the number of atoms or molecules that are being produced or consumed. When performing these calculations, we need to ensure that we have the same number of atoms of each element in both the reactants and products in order to obey the law of conservation of mass. The best way to do this is to use the number of moles of each substance. This means that if we are given an initial quantity as mass, we would need to divide by the molar mass of that substance to find the moles of that substance. If we are given the number of atoms or molecules as an initial quantity, we would divide by Avogadro's number to find the moles. Conversely, we would perform the opposite calculations to convert from moles to mass or number of atoms or molecules. Let's look at the following reaction where methane, CH4, reacts with oxygen gas in a combustion reaction to form CO2 and water. If we begin this reaction with 35.00 grams of methane, how many grams of water are produced? The very first step is to ensure we are working with a balanced chemical reaction. If we wanted to balance this reaction, we would find that one molecule of methane reacts with two molecules of oxygen. It produces one molecule of carbon dioxide and two molecules of water. In this problem, we are given the amount of methane and asked to find the mass of a water formed. Therefore, our first step must be to convert the mass of methane to moles. We do this by dividing by the molar mass of methane, which is 16.05 grams per mole, making sure our units cancel out. We would also know from the coefficients of the balanced equation that for every 1 mole of methane consumed, it produces 2 moles of water. We can multiply by this ratio of coefficients to convert moles of methane consumed to moles of water produced. Our final step is to convert the moles of water produced to mass in grams. This means that because we are starting with moles, we need to multiply by the molar mass of water, which is 18.02 grams per mole. To find the final mass of water, when we plug these values into our calculator, we can determine that under these conditions, the reaction produces 78.59 grams of water. In this example, we calculated what is known as the theoretical yield of the reaction, which is the amount calculated assuming 100% conversion under perfect reaction conditions. In reality, when performing these experiments, the actual amount obtained is often lower than the theoretical yield. This amount, which is based on experimental data, is known as the actual yield. We can compare the actual and theoretical yields of a reaction by determining the percent yield, which is equal to the actual yield divided by the theoretical yield times 100. Therefore, if we were to look back at our combustion example and found that when we performed the reaction in a lab, we measured that only 56.45 grams of water were produced. That would give us a percent yield of 71.83%. Another concept we would need to be aware of when performing these calculations is the limiting reactant. This is the idea that when a reaction involves two or more reactants, one will be completely consumed before the others. This reactant is known as the limiting reactant. Any reactant that is left over once the limiting reactant is consumed is known as excess reactant. It is important to note that once the limiting reactant is exhausted, the reaction cannot continue and will not occur further, meaning the limiting reactant dictates how much product is produced. For example, if we wanted to make veggie burgers for a party and each veggie burger is made up of 1 patty, 2 buns, and a slice of cheese. If we had 7 patties, 16 buns, and 10 slices of cheese, how many complete burgers could we make? We can see that we will run out of patties first, making it the limiting reactant. Once we run out of patties, we can no longer make any burgers. We also can observe that if we use all of the patties, we could only make 7 veggie burgers in total, meaning our theoretical yield is 7 burgers. Let's now apply this to our previous example with the combustion of methane, but now we are starting with 35 grams of methane and 42.50 grams of oxygen gas. What will be our limiting reactant and theoretical yield for this reaction? Once again, we need to make sure we are starting off with a balanced chemical equation. Notice that we do not know which of our reactants is limiting and which is present in excess. Therefore, what we need to do is calculate the theoretical yield for each reactant amount, meaning we need to perform 2 separate calculations. The reactant that produces less product will be our limiting reagent because it will have been completely consumed before the other. Our first calculation will be in respect to methane. These steps will be the same as before, converting the mass of methane to moles, then using the ratio of coefficients to convert to moles of water, and finally using the molar mass of water to convert to the mass of water. This gives us the same yield as before, which is 78.59 grams of water. Now we need to do a similar calculation, this time starting with the mass of oxygen gas. We divide by the molar mass of oxygen to convert to mole of oxygen gas. Next, we use the ratio of coefficients in our balanced equation, which is 2 molecules of oxygen to 2 moles of water produced. Well, finally, we use the molar mass of water again to find the mass of water produced. When we perform this calculation, we see that it would produce 23.93 grams of water. Since this mass of oxygen will produce less water, it will be completely consumed first, making it our limiting reactant, and our theoretical yield under these conditions is 23.93 grams of water. Note that we cannot produce more than this amount because there will be no more oxygen gas left to react. This amount is also less than the amount of water that would be generated if methane was completely consumed, meaning that some unreacted methane will be left, making it our excess reagent. These stoichiometric calculations can take a variety of forms and use different types of measurements, including masses, volumes, number of particles, and more. Therefore, it is important to practice working through different types of these calculations to better familiarize yourself with the steps. As a review, today we will discuss how to use balanced chemical equations to predict the amount of substance that is consumed or produced by a chemical reaction, as well as percent yield and limiting and excess reactants. Thank you for joining me and have a wonderful day. Thank you.